Hello and welcome back to another A-level maths revision video. Now, at this point here, it's a little bit bittersweet, right? Because this is the very last predicted paper here as part of this year's exam series. So we're pretty much there now, and A-level maths is pretty much complete. Okay, just one more paper to go. So that is the applied paper, 50% stats, 50% mechanics. Hopefully you are familiar with the format of how this paper works. If you're not, I am a little bit worried, but that shouldn't hopefully be the case, right? So first thing to mention here, I haven't included the cover kind of like page on the screen here. Not that it is particularly relevant, but I do kind of normally do that. But that will be adjusted before I upload it on the website. So if you're watching this video here then, the actual paper is already live on our website, AJMaths.co.uk, alongside an additional free predicted papers here for paper free, right? The applied paper. So if you're also a member as well on our YouTube channel, so as part of the revision video tier, we will also send you all 4 predicted papers, but you will need to email us for those. So just drop us an email at support@ajmaths.co.uk, and I will email over all 4 predicted papers pretty much straight away, right? So just drop us an email, and I'll get those over to you as soon as I can, right? But other than that, I don't think there's really too much more that I wanted to say here. Obviously, best of luck. So paper 3 is on Thursday, right? So that's pretty much just a few days away now at this point here. But yeah, best of luck. Let's not waste any more time then. And let's just get started with question 1. All right, so let's just get started here then with question 1. So we have a factory that produces light bulbs. Each light bulb is tested. It's either faulty or not faulty, right? Otherwise, what is it? For each light bulb, the probability that it's faulty is 0.08. And a quality inspector tests 20 light bulbs from one batch. So for the first part here then, part A, we want to find these 2 probabilities here. So let's just start then right at the very top here. So part A then, this is split into part 1 and part 2. So for part 1 then, we want to find the probability that exactly 2 light bulbs are faulty. So we need to recognize here then the distribution that we're working with here. So if you see it mentioned mean and standard deviation, then it's clearly the normal distribution. If not, it's going to be the binomial distribution, right? As we can see here, we've got this probability. That is the probability of success, which isn't really success because it's going to be faulty, but you know what I mean, right? So I'm going to choose X here as our random variable. It doesn't really matter, but the convention here is to just choose X. So X follows a binomial distribution. The parameters here are N and P. N is the sample size, which is 20 here. So N is 20. And then for P here, that is this probability of success, which is 0.08. Just like that, right? So for part 1 then, we want the probability that exactly 2 light bulbs are faulty. So that is the probability then that X here, our random variable, is equal to 2. That would be exactly 2 being faulty, right? So you can do this by hand here if you really want to. Why you would do that, I don't know. Just grab a calculator, because you can just throw this all into your calculator and it will give you the correct probability. So don't bother doing it by hand unless you need to for whatever reason. But anyway, how would I do this on my calculator? So we're going to stats mode and obviously distribution. What I want here then is the binomial distribution. So that's going to be BINM on most calculators. I then want BPD as opposed to BCD because it's not a cumulative probability here. It's exactly equal to 2, right? That's going to be BPD. The way that I like to remember that is P is precise. It's exactly 2. So it's going to ask for 3 different things then. It's going to want N. So N here is just a sample size, right? That's 20. It wants P, the probability of success, which is 0.08. And it also wants X here. So X in this case then is this value, which is 2. Press enter. And bosh, that is your solution. And if you've done this correctly, then we should get the same thing here. If we don't, there's a problem. We should get 0.271. There we go. Nice and easy. So that's A part 1. Pretty similar for A part 2 then. But just be careful here because we want the probability that fewer than 4 light bulbs are faulty. So what I'm looking at here then is the probability that X, our random variable, is strictly less than 4, right? If it's fewer than 4 light bulbs, that is strictly less than 4. And that is the same then as the probability that X is less than or equal to 3. Okay? So again, pretty similar, but just be careful here. It's not BPD. It's now a cumulative probability here. So it's BPD. CD. Okay. Again, this is almost the same here. The only thing that changes is x now. So x here is 3. So you put x equals 3, n is 20 again, p is 0.08. Put that into your calculator, and again, bosh here. What you should get then is 0.929. There we go. Nice and easy. So that's the first 2 marks. So in fact, that's 4 marks. Yeah, how easy is that, right? So that is question 1, part A done. We're not finished here though, because we've also got part B. So let's just quickly read through this here. So what have we got then for part B? So it says, over a month, the factory produces 1,000 light bulbs. Good work, team. The manager of the factory decides to use a normal distribution to estimate the probability that at most 90 of these light bulbs are faulty. So I've got 2 different parts here for B as well, B part 1 and B part 2. So for B part 1 then, it just says find the mean and variance of this normal distribution. So clearly what we're going to do here is just use an approximation, right? So for the approximation here, I'm going to use a different let to begin with for our random variable. Let's just use y here. Again, it really doesn't matter, but we've already used x here. It makes sense to choose the next letter in the alphabet, which is y. So y here will be approximately normally distributed. You can just use tilde again here, this funny little squiggle. We should have another line underneath it really, but I'm going to be lazy. So y is approximately normally distributed here. Now in terms of the parameters then, the 2 parameters here for a normal distribution are the mean and the variance. For the mean here then, using a binomial approximation, mu, that's the mean here, that is n times p. And then for the variance here, that is, so that's np times then 1 minus p, just like that, okay? So np here, that's going to be 1,000, because that's our sample size here, 1,000 light bulbs. And we times that by the probability of success, which again, it's not really a success, but it is this probability here of 0.08. So 1,000 times 0.08, and that gives us 80 there. Okay, so the mean here is 80. And then for the variance here, it's going to be 80 because NP is 80. But I times that by 1 minus P, so it's going to be 1 minus 0.08. We times that by 0.92. So 92% then of 80 here, that gives us 73.6 there. Okay, and that is the variance. So 73.6 there for the variance. Close that bracket. So that's our model here then for part B. So that's B part 1, giving us the mean and variance of this normal distribution here. That's absolutely fine. And then for B part 2 here, it just says then estimate the probability that at most 90 light bulbs are faulty. So for B part 2 then, what we require here, so we require the probability then that y here, because we've changed the model now for y instead of x here, is less than or equal to 90, right? Because what we're looking at here is the probability that at most, so at most here, 90 light bulbs are faulty. So that's going to be less than or equal to 90, like so. Now, just be careful here, because when you approximate, as we've done here in part B, we need to apply what we call a continuity correction. Now, this can cause problems for some students, kind of remembering which way around the continuity correction is applied. So what I want here is the probability that y is less than or equal to 90, right? So we need to include the 90 here. So we either go 0.5 bigger or 0.5 less than 90. Now, because I want to include the 90 here, we're going to go 0.5 bigger. If I go 0.5 smaller, then we omit the 90, right? So if you find it easier, just draw a number line. You don't have to draw a number line. It's a very basic way of thinking about it, but if it does help, just do that. You won't get judged, I promise you. So, like I said, if that's the case, just draw the number line. But either way, it's relatively straightforward. So applying the continuity correction, I'm just going to apply C.C here for continuity correction. What we get here then is the probability then that y is straight less than 90.5, like so. Okay. And at this point here, we can just simply use our calculator again here. You don't need to do this by hand. So just grab your calculator here. Obviously for this one now, it's the normal distribution, not the binomial distribution. So again, just be careful for that. There's going to be NCD here. And it wants a few different things. So it wants the mean, so that's mu, which is 80 here. So mu is 80. It wants the standard deviation, which is the square root then of this here. This is the variance, right? So that's root 73.6. 73.6 there. And it also wants a lower and an upper value here. So for the lower and the upper, I'll do those to the left-hand side here. So lower and upper. What are those? So for the lower here, I'm just going to choose an arbitrarily small value, right? Because what I'm looking for here is the probability that y is straight less than 90.5. So my lower value here is just something arbitrarily small. What I like to normally do here is just put a minus then and a load of 9s. Something like that is absolutely fine. And then for the upper value here, we put this value in, right, of 90.5. Input all of that, press enter. And again, one final bosh here for question 1. Bosh, we get our solution of 0.890. So 0.890 there. And there we go, lovely jubbly. So that's a solution to B part 2. That's a solution to B part 1. This here is A part 2 and A part 1. And there we go then. So hopefully nice and straightforward just to get us started right. And that gives us the solution to question 1. All right, so moving on to the next question here, then question 2. As we can see on the screen here, we have a question on the PMCC, or otherwise known as the product moment correlation coefficient. That's always a tongue twister. So what we've got then for question 2 here is 8 students who sit 2 different music tests. So one of the tests is on the theory part, and the other is a performance test. So their marks are shown in the table below here, as we can see. So for part A then, it's just a 1-mark definition type question. It just says, state what is measured by the PMCC. So again, it's just 1 mark here. It isn't really going to make or break your exam. But all things considered, it is a pretty easy 1 marker. So for the PMCC here, what we're saying then is the PMCC measures the type and strength of linear correlation here between 2 variables. Okay. Let's just try and summarize that here then. So the PMCC measures, so it measures here the type and strength of linear correlation between 2 variables. So the PMCC measures the type and strength of linear correlation. And that is important here that we state that this is linear correlation here. Linear correlation between 2 variables. Between, oops, I can't spell. I was going to put between. There we go. English is hard. Between 2 variables. There we go. Between 2 variables. Okay. That's the first mark in the bag there. Hopefully nice and easy. So for part B then, another nice easy 1 marker here. It just says find, using your calculator, the product moment correlation coefficient for these data, giving your answer to 3 significant figures. So for part B then, as it says, right, we're just going to simply use our calculator here. Nice and straightforward. If you don't know how to do this using your calculator here, then make sure that you do know how to do this, because I'm going to show you how to do it anyway. So you grab your calculator, go to stats mode, and in your stats mode here, you should have kind of like a few different lists that you can enter data into. Okay, so on mine, I get list 1. I've then got a line here, list 2. Another line here, list 3. And that just keeps going on and on, right? So on and so on. So in list 1 here, what we do then is we enter this row of values. So 8, 14, 11, 19, 6, so on and so on. That's going to be 8, 14, so on and so on, up to the last one, which is 20. Like that. And then we do the same here in list 2. What is important to mention here is these should match. So it should be 8 and 9, 14 and 13, 11 and 12. Don't enter these randomly here. Okay. So again, it's going to be 9, 13, so on and so on. What's the very last value here of 19? Okay. There shouldn't be anything in list 3. I just kind of put that there just to show you what it would look like on your calculator. So you can just ignore that. Okay. We enter both of those. So what I want here then is regression. And you can either do ax plus b or a plus bx. It really doesn't matter. You want linear regression, okay? You've got quadratic regression and all the other different types of regression. We want linear regression here, and then it's either a plus bx or ax plus b. Again, it really doesn't matter because all we're kind of bothered about here is just r, okay? R here being the PMCC, the product moment correlation coefficient. So enter that into your calculator. It's ax plus b or a plus bx. It really doesn't matter which you do, but either way, r here. And by the way, this is the free SF here, as it asks for them. That is going to be 0.980 there, okay? Don't do it, pen. We've got a little bit more to go here. So that's part B complete. We've got part C here. So let's just do this underneath then. This pen. So it just says, a teacher claims that students who do well in the theory test also tend to do well in their performance test. So for part C then, it says test this claim at a 0.05 significance level, stating your hypotheses clearly. So for part C then, it's a hypothesis test, right? So with any hypothesis test here, we should always just start with the hypotheses. Hopefully that is obvious. So we've got H0 and H1 here. So we'll start with H0. Let's write H1 underneath anyway. So for H0 here, what we're looking at here then is the product moment correlation coefficient. For that, we use a Greek letter here. Hopefully you do recognize the Greek letter, and that is rho, okay? Kind of like a P that's fallen on its side here. Something like that, okay? So we say that rho here is equal to 0. We're testing for 0 correlation essentially there for H0. And then for H1 here, we need to decide it's either going to be greater than, it's either going to be less than, or not equal to 0. Now, if we're saying that students who do well in the theory test also do well in the performance test, then what we're saying here is that rho is strictly greater than 0, right? This would indicate here positive correlation. If you do good in one, you're also going to do good in the other test, right? So that's our hypotheses there stated clearly. Bosh, job done. What I also need here is two other things. I need the test statistic, which we've already kind of evaluated here in part B, as we can see, rather messily. So the test statistic here, T.S, I will abbreviate it to. That is 0.980. It's this value of R here. That's 0.980. Nice and easy. And what I also need here is the critical value. So what is the critical value, I hear you ask then, for this problem here? Well, to find the critical value, you do also need your formula booklet. For the relevant part here, as we can see then, I have included it on the screen. But what I would recommend here is just grab a formula book to hand and make sure that you know how to find this using your own formula book, because the last thing that you want here is to be in the exam and not realize that you can't do this, okay? It's really straightforward, but if you don't know how to find the critical value here, then you're going to fall apart at the very end of the hypothesis test. So to find the critical value here, we refer to this page here, which has the product moment correlation coefficient. Just be careful. On the right-hand side, I've kind of omitted it, but on the right-hand side here, we have something known as Spearman's rank. That is completely different, so make sure that you're reading from the correct part of the table here. So the level then, that is 0.05. So we're in this column here, okay? What is the sample size then? As we're told here, we've got 8 students, right? 1, 2, 3, 4, 5, 6, 7, 8. So N here is 8. We're in this row. So go across and then go down until you intersect here. So you would go down like so. You would also go across like so. And once we intersect here, we know that we found our correct critical value, which would be this one here. Okay. This one here, right? 0.6215. I kind of butchered a little bit with my not very neat working, but 0.6215 there. Okay. And that is the critical value. So to finish with here, what we do then is we compare the test statistic to the critical value. So 0.980 is greater than 0.6215. So what we say here then is we're going to reject H0, right? Because there is sufficient evidence to suggest that the teacher's claim is valid, okay? Basically, if you do better in the theory test, you're also going to do better in the performance test and vice versa, okay? So as we just said then, you reject H0. Make sure that you always give your conclusion kind of, or link it back to the context of the question here. Just to finish with, you can't just say reject H0 or accept H0 and call it a day. Make sure then, again, that you link it back to the context of the question. So reject H0 here. To reject H0, there is sufficient evidence. There is sufficient evidence. Sufficient evidence. Sufficient evidence to suggest that the teacher's claim, is it a music teacher? Who is it? A teacher. So the teacher, the teacher's claim is correct. Correctamundo. There we go. Okay. There we go. So just give a conclusion there to finish with for any hypothesis test, as we've demonstrated there. And then finally for part D here, it just says, give an interpretation of the value 0.05 in your hypothesis test. So what does this significance level here actually mean? So most students kind of, go through A-level maths in, not really understanding what a significance level really, represents here, I should say. If you're going to do A-level further maths and you're going to do further stats 1, you learn about this in a lot more detail with quality of tests and, significance levels. The A-level maths is kind of just, you're given it and you're just kind of told to take it at face value. But again, if you're going to do A-level further maths, you'll learn a lot more about this in greater detail. But I can't really explain that all in one video here just for one simple mark. All I want you to understand here then, for part D, and I will just quickly clear the screen. So for part D then, all we say here is there is a probability of this level, so 0.05, that the null hypothesis is true. Okay, so there is a probability. There is a probability of, I should say, 0.05. So if that was 0.1, for example, it would be a probability of 0.1. You get the idea. That the null hypothesis is true. Okay, and there we go. Again, it's just one mark. It's unlikely to kind of boost your grade significantly. But, it's an easy one marker, so we want all the marks that we can get, right? And there we go. So, again, keeping things pretty simple, that was question 2, hopefully nice and straightforward. Now, moving on to the next question here, then question 3. As we can see on the screen, this question is a little bit spooky for 2 different reasons. So, for the first part of this question here, then part A, it's based on a large data set. I know, painful. I'm not sure which donut came up with the idea of the large data set, but they are a donut. Pass it on. So for part A then, let's just quickly work through this here. So for A part 1 then, all we want to do here is for the large data set, state the units of the following 3 measures here. I'm going to be completely honest, I didn't put too much thought into the large dataset question here because I absolutely despise it. It is disgusting. So yeah, this is the best I was coming up with for this paper here. We'll just roll with it because you do need to know the units here of these different measures, right? So it's still some good practice, but it is what it is. So daily mean pressure then, what are the units for that? So we can either just say HPA, or this is better known as hectopascals. I know, right? Absolutely amazing. So HPA like that, or hectopascals. They're the same thing. We should just really call it hectopascals. We'll just see aware here. Same thing. So hectopascals. Is it a capital P? I'm not sure. Is it a name? I don't know. It'll do though. You won't get penalized either way. So that's A part 1. A part 2 then. So this is for daily mean total cloud. So that is octas. So you just need to remember that as octas, O-K-T-A-S, like so. So octas there. And then finally for A part 3 here. Daily maximum gust, that is measured in what we call knots. So knots here. So knots, like so. Okay, so that's part A, part 1, part 2, and part 3. As I said, I didn't really put too much thought into it, but you do need to remember these units here. So still some good practice, right? So that is part A complete. Now for part B then, this one is also a little bit spooky. The reason why is because conceptually, part B here is pretty straightforward, but the way that this is presented, it looks a little bit different, and I'm sure as you work through this paper here, this will catch many of you out watching this video, right? So what I would recommend here is that you pause the video and give it a quick go. But as I said, I'm sure it will cause a problem for many students. So this question here is kind of like my curveball question for the paper anyway, or at least for the stats part. So let's just start then with part B underneath here. So it just says then, the following information about 8 observations of Y is shown below. So we've got this here and this here. So for 6 marks then, what we want to do here is calculate the mean and standard deviation of Y. So like I said before, conceptually, this isn't too bad. What we're going to do here is just a little bit of coding, and I don't mean Python, R, anything like that. I mean statistical coding. So what I'm going to do here is just replace then this here, and it's also the same here, right? But it's just squared. So I'm going to replace that with just some variable. I'm just going to call it Z. So I'm going to let Z then. So let Z here be equal to, so it's going to be Y minus 140 over 5. I appreciate that it is Y subscript I. Really, I should call this Z subscript I, but I am a little bit lazy. It doesn't really matter too much, but I'll just call it here Z and just Y here. So Z is equal to, so it's going to be Y minus 140 over 5, like so. Okay. So what I know here then is the sum of Z here from I equals 1 to 8 is 24. So let's make a note here. So what we know then is the sum of Z here, the sum of Z is equal to 24, because this is the summation here of Y I minus 140 over 5, which we've just replaced with Z. So sigma Z is 24. And what we also know here is the summation then of, so this is Z squared, right? So the summation of Z squared here is equal to 152 there. Okay. What we also know as well is N is 8, right? There's 8 observations here. So N is equal to 8. Right. So we're off to a good start here. Now, what I want then is the mean and standard deviation of Y. So what I can do here then is just rearrange this equation, making Y the subject. So if we do that then, and I'll do that over here, by the way. So what I'll get here then is times both sides by 5. So I get 5Z is equal to Y minus 140. So to finish with then, just add 140 to both sides here. And Y is equal to, so it's 5Z plus 140, right? Like so. Okay. Now, before I continue from this point here, what I also want to find then is the mean and standard deviation in terms of Z. Okay, because what I know then is sigma Z here is 24, and I also know sigma Z squared is 152. And you can probably see then where this kind of goes from here, right? So from this point here, it's pretty straightforward. I think it's just making kind of like this first step here and, you know, replacing this and this here with some kind of different layer such as Z, okay? But anyway, let's just stop waffling here. So Z bar then, so that's the sample mean here for Z. That is sigma Z over N, the sample size. Well, sigma Z is 24. And that is over N, which is 8. How many 8s go into 24? Well, that is just simply 3. So Z bar here is 3. And for the standard deviation then in terms of Z, so SZ or sigma Z, it doesn't really matter. It should really be SZ, but whatever. That is going to be then the square root here. It's the square root here of, so it's sigma Z squared. That's over N. And then what we do here is we minus Z bar squared, like so. Okay. So again, what would I get here? I've got sigma Z squared, that is 152. 152. That's over N, which is 8. And then minus here, Z bar squared. So whatever you got for Z bar, just throw that back in, right? If you didn't get 3 for whatever reason, then you just continue with your working here. Minus 3 squared, like so. So what does this give me here? 152 over 8. What is that? That's going to be 19. That's going to be 9. That's going to be root 10. That gives me 10 there, like so. And then I've got root 10 here for the standard deviation in terms of z, right? So let me just double check this up to now. Z bar is 3, yes. And then, yeah, that was 19, right? I did have difficulties calculating that off the top of my head. My mental maths is not good, but hashtag quit maths. So I've got root 10 there. Perfect. Now, I'm going to go back to this here. So y is equal to 5z plus 140, right? If I want the mean of y, then y bar is equal to 5z bar plus 140, right? So in that case, then, for the mean of y here, so therefore the mean of y, so for the mean of y here, that will be 5 times z bar, which is 3. So I get 5 times 3 plus then 140, right? So 5 times 3 is 15 plus 140, and we get 155 there. Perfect. So that is the mean of y. And then to finish with here, we also want the standard deviation of y. So let's just do that as well underneath here. So standard deviation of y. I'll call this standard dev of y, because why not? So for the standard deviation of y here, well, adding or subtracting here has no effect on the standard deviation, right? So for the standard deviation here of y, it's just simply what we got here for sigma z, but we times it by the 5 here. Okay, so it's going to be 5 root 10. So 5 root 10, or whatever that is, as a decimal. I didn't calculate that, so let me just quickly do that on my calculator, which I don't have to hand, so I'm going to use my phone. So 5 times then root 10. And that gives me 15.8 there to 3 significant figures. So 15.8 there. And there we go. So this here is the standard deviation of y. And this here is the mean of y, right? And there we go. So as I said, part B, conceptually, is pretty straightforward. It's just a little bit on coding, finding the mean and standard deviation using summary statistics. All relatively straightforward. But in this form here, it might cause problems. So if you do get something that looks a little bit different, such as that, don't panic. Just use, your intuition to tackle and approach a question such as that one, right? Well, there we go then. So that gives the solution there to question 3. So for the next question here then, question 4, as we can see, we've got all this waffle here. This is going to be fun, right? So let's just quickly read through, or at least start to read through some of the waffle here. It's always a good starting point. So what I've got here then is a large number of runners who take part in a 10-kilometer race. A random sample of 400 runners is selected. Now, the times of runners in this year's race are modeled by a normal distribution with this here as the mean. Let's highlight that. That will be important. And the same here then for the standard deviation. We'll highlight that too. So for the first part then, part A, what we want to do here is just find then the following 3 probabilities here, right? This is just 3 marks. You shouldn't really be expecting to do too much work here. The reason for that is because we can just simply use our calculator, right? Our trusty old calculator to save us here all the pain of having to do this by hand. So I want these 3 probabilities here. So for the first part then, what I clearly need to do here is just define then a random variable here to model this situation, right? The scenario that we're dealing with here. So the general convention is that we just choose X, but if you want to be fancy for whatever reason and choose something different, then go ahead and do that. But I'm going to choose X here as my random variable here. So X then, it will follow a normal distribution because we're told it's a normal distribution, right? Why not? So X follows a normal distribution. For the normal distribution here, you have 2 parameters. You've got the mean and the variance. So for the mean then, we're told that it's 28.6, right? So we jot that down first. And then the variance here, well, the standard deviation is 4. So the variance then is the square of that. So 4 squared, like so. Okay. So for A part 1 then, what I want here is the probability that X, our random variable is less than 25, right? Less than 25 minutes. Now, as we already said then, just use your calculator here. Okay, so obviously it's the normal distribution. You've got a choice then of NPD or NCD. For the normal distribution here, what I want you to remember is it's always NCD. So always NCD. It's never NPD for the normal distribution, always NCD. So it's going to ask for 4 different things here. It's going to ask for the lower, it's going to ask for the upper. Just make a note here in the top right corner. So lower, it's going to ask for the upper. It's going to ask for mu here, the mean, and also sigma, the standard deviation. So I'll come back to the lower and the upper in just a moment. For mu and sigma here, nice and straightforward then. We're already given those in the question, right? So mu here is 28.6. And then for sigma here, so just be careful. This is the variance. So the standard deviation here, as we're told in the question, is just 4, right? So just be careful for that. It will throw your answer. Now for the lower and the upper here, that is dependent on the context of the question and the probability that you want to find here. So what I want here then is the probability that x is less than 25, right? So if it's less than 25, this number here goes into the upper, okay? And if it was greater than 25, then that number would go into the lower. So just be careful that you get it the correct way around here. It is easy to get that mixed up. So the upper value here, I can't speak anymore, that is 25, like so, just this number here. And now for the lower value here, we just choose an arbitrarily small value. What I like to do here is just put a minus and then a load of 9s here, like so, okay? But anything that's just arbitrarily small here will suffice, okay? Press enter, and what we get here then is this probability. And if you've done this correctly then, what you should get here is 0.184. Bosh, nice and easy, right? So that's A part 1. A part 2 then, even easier because you actually don't need your calculator for this. A common mistake here is to try and use NPD because it says exactly 27 minutes. But be careful here because the normal distribution is a continuous distribution, right? And for a continuous distribution, we can't have the probability then of our random variable x here being equal to an exact value, okay? So x here cannot be equal to 27. That probability is just 0, okay? Like so. So you don't need a calculator for this. If you get something like this here for the normal distribution and it's equal to a specific value, such as it is here for A part 2, then don't forget that it's always just 0, right? So that's A part 2 complete. And then for A part 3 here, even easier. Well, easier than part 1 because for the lower here, that's 27. The upper is 30. Mu and sigma don't change, right? Press enter again here. So it helps if I actually write down the probability. So between 27 and 30 here, again, just press enter with the correct values in here. And what we get then is 0.292 there. Like so, okay? And there we go then. So that's the solution to A. So part 1, part 2, and part 3. Now for the next part then, part B, we'll just do this underneath here. As I can see, we've got even more waffle here. So let's just quickly read through this. So it just says then, historically, the mean time for runners in this 10-kilometer race has been 29 minutes. Now, a coach believes that the mean time of runners in this year's race is less than the mean time of runners in previous years. The times of runners in this year's race are modeled by a normal distribution with a standard deviation of 4 minutes. So what we want to do here is just perform a hypothesis test, right, at the 5% significance level, whether or not this sample provides evidence to support the coach's belief. Blah, blah, blah. The usual state hypotheses, make it clear, all that good stuff, right? So it's a hypothesis test. As I always say then, for a hypothesis test here, we should just start by defining the hypotheses. It's always a good starting point. So H0 here and H1. So what we test in here? Well, we're testing the mean of a normal distribution, right? So that's the parameter mu. I put mu here for both of these hypotheses. So what are we actually testing here? Well, what we're testing here then is the coach's belief that the mean time of runners in this year's race is less than, I'm going to highlight that because that's important. So it's less than the mean time of runners in previous years, where the mean in previous years has been 29 minutos. So mu here is equal to 29. And then if we're testing that it's less than, then mu here is strictly less than, right? So mu is less than 29, like so. Okay. Now, for the next step here, what we do then is we assume that H0 is true. So, as I've just said then, we assume that H0 is true. Now, if H0 is true then, what does that tell us here? So, I'm going to take X bar here, and this will follow a normal distribution. So X bar follows a normal distribution here. Now, because we've assumed that H0 is true here, then the parameter or mu here is 29, right? So that value of mu is 29 because we assume that H0 is true, where H0 is saying that mu is equal to 29. That's all well and good. And now for the variance here, just be careful. So what you might put here is just 16, but just be careful here because we do need to account for the sample, right? What I've got here is a random sample of 400 runners. So what I do here is I take the variance, which is 16, and I divide that by the sample size, which is 400. So that is 16 over 400, like so. Okay. Now, what I need here then, pretty much to finish with, is just the test statistic. Okay. It's always a bit of a tongue twister. So to save me writing this out in full here, I can just abbreviate this to T.S here. Okay. This is the test statistic. So what is that? Well, that's based on the evidence here that we've got given in the question, right? So what I know here, and this kind of comes from the previous part of the question, so just be careful. You do sometimes need to kind of like dip back into the previous part of the question here. What we're told then is the times of runners in this year's race are modeled by a normal distribution with this here as the mean, so 28.6, right? So that's my evidence here. So we're testing the evidence, right? So this here then is the probability that X bar. Now in terms of the inequality here, if H1 is less than, then the evidence here is less than as well. If it was greater than, it would also be greater than here as well, right? So just remember that for a one-tailed test. So what I'm testing here then, as we've just said, is the evidence. So that's going to be 28.6 there, like so. Again, just roll this into your calculator using NCD here. Make sure you just adjust this correctly. So the other thing to mention here is for the standard deviation, that would be the square root of this here, right? So that's going to be 4 over 20. Just be very, very careful for that. It will trip you up if you're not careful. And if you do all of this correctly, then what you should get here is 0.0, so 0.0228 there, like so. Okay. So what do we do with this here then? Well, we compare this to the significance level, right? Now, what you can also do here is use Z values, but I don't like that as a method personally. I find this, a lot more intuitive to use the P values as we call them. So I find the test statistic using the evidence as we've done here, and I get this probability, and then I compare that to the significance level. That's the way that I like to do it. But as I said, if you prefer using Z values, then that's absolutely fine as well. We should arrive at the same conclusion here. So I compare this here then to 5%. So it's a one-tailed hypothesis test, so you don't need to divide this by 2. So just be careful for that as well. So 0.0228 is smaller than 0.05, right? 5% there. So what does that tell us then? Well, what it tells us here is we need to reject H0, okay? So therefore then, reject H0. And again, as always with any hypothesis test here, we should kind of go back to the context of the question rather than just saying reject H0, jobs are good. You do need to give some sort of context here for the question, right? I know it's annoying, but it shows the examiner that you do understand what's actually going on here. So reject H0, we have sufficient evidence then to suggest that the coach's belief is true, right? So sufficient evidence, So sufficient evidence here. If you want to as well, you can say at the 5% significance level. That's always a nice little touch there. But I'm lazy, so I won't do it. But sufficient evidence to suggest that. The coach's belief is true. Okay. And there we go. You can give it a little bit more, or you can give a little bit more detail for the conclusion if you want to. You know, but I think this here is absolutely fine, right? It doesn't need to be a novel. Keep it simple. Okay, so that's the solution to part B. And then finally for part C here, it just says, explain with specific reference to the parameter P why this distribution here might not be a reasonable model for the number of Rapid Runners members who are invited to compete in the regional event. So I should have read this here beforehand. So Rapid Runners Running Club, that is a tongue twister, enters its 5 fastest runners and 5 beginners to take part in the 10-kilometer race. The fastest 15% of the runners in the race are invited to compete in a regional event the following month. All right, so why is this a problem here? Well, it's nothing mathematical, essentially. Think about this more in a kind of like real life, common sense context, because, so for part C here, if you think about this here then, if I've got the 5 fastest runners and 5 beginners, the probability of success here is going to be completely different, right? Unless those 5 beginners have absolutely amazing genetics and they can run this 10-kilometer race with no problem, then it's unlikely they're going to be as quick as the 5 fastest runners, right? So obviously one condition here, and it kind of gives you the clue here with reference to the parameter P, is probably here. One condition for the binomial distribution to be a good model is that the probability of success must be constant, right? It doesn't change. But as we've just said then, the 5 fastest runners and the 5 beginners here, that probability of success, it's likely to be different, okay? So what I'm going to say here then is the probability of success here. The prob of success will not be constant. Will not be constant. Not be constant, as we have 5 beginners. 5 beginners. And the 5 fastest. Okay. And therefore then, this here, therefore, not reasonable. Not reasonable. Would have helped if I had a little bit more room, but that will do. There we go. Okay. And there we go. So as you can see, as I said before, there's quite a bit of waffle for this question here. This one alone has took us over 15 minutes. I know I do waffle quite a bit anyway, so feel free to kind of put this on double speed if you want to. But hopefully that did make sense, and that gives us the solution here then to question 4. Now, question 5 then, as we can see on the screen here, is on what we call discrete random variables. As an A-level maths topic, this gets somewhat neglected because it's a first-year topic, but it is still important that you know how to deal with questions such as this one here. So what I've got here then is the probability distribution of the discrete random variable x, which is given as the following here. So we've got this table where k is just simply a constant. So for the first part here then, so this is question 5, part A, what we want to do here then is find, in terms of k, the probability that x is not straight less than 5, but less than or equal to 5. I can't read, so that's not promising. But for the probability then, x is less than or equal to 5 here, what would that be? So that is going to be then the probability that x is equal to 3, right? The probability that x is equal to 3, our discrete random variable here, is equal to 3, plus then the probability that x is equal to 5, okay? Plus the probability then that x here is equal to 5. Well, the probability that x is equal to 3 here, that's 0.6 minus 2k. We've got 0.6 minus 2k. And then for the probability that x is equal to 5 here, that is just simply 3k, right? So we add those together. And now let's just simplify here. 0 0.6, well, there's nothing else that we can add or subtract from that, so it's just simply 0 0.6. And then minus 2k plus 3k, that just simply gives us plus k there, right? And there we go. So nice and straightforward there, I guess, is the first mark for this question here. Now for part B then, let's just continue underneath here. It just says state the range of possible values of k. 2 marks for this, right? So as we can see here then, for the 3 different probabilities here, they're all in terms of k. So I've got 0.6 minus 2k, 3k, and 0.4 minus k, right? Now, what you should be aware of here then, for a discrete random variable such as this one here, these probabilities are non-negative basically. Okay, so they must be greater than or equal to 0. Okay, so what I can say here then is 0.6 minus 2k, that must be greater than or equal to 0. I'll come back to that in a moment. I can say the same here then for this probability, so 3k. So 3k is greater than or equal to 0. And also 0.4 minus k, again, that must be greater than or equal to 0. So 0.4 minus k there is greater than or equal to 0. So what I'm going to do here then is just solve these 3 inequalities here for k, right? And then hopefully the answer will be a lot easier to see at that point, right? So you would add 2k to both sides here. So 0.6 is greater than or equal to 2k. That is the same then as saying that k here is less than or equal to 0.3, right? Dividing both sides by 2 there. So k is less than or equal to 0.3 for this inequality. For this one here, nice and straightforward then, k is just simply greater than or equal to 0, just dividing both sides by 3. We get this here. And then finally for the very last inequality here, so 0.4 minus k is greater than or equal to 0. Pretty similar to the first one here, right? 0.4 must be greater than or equal to k. In that case, then what we're saying here is that k is less than or equal to 0.4, right? So less than or equal to 0.4. Now, once we've got each solution here to the individual inequalities, right? I'm hoping the solution here is a lot easier to see, right? K is greater than or equal to 0, as we can see here. And I've got these two here. So k is less than or equal to 0.3 and k is less than or equal to 0.4. Okay. But to satisfy then all 3 inequalities here, the range of possible values of k then would simply be, this would be between 0 and 0.3. Okay. And there we go. So let's just kind of put a bubble around this here just to indicate then that this here is our solution. There we go. That's the solution to part B. And then finally for part C here, let's just do this over on the left-hand side here. So it just says then show that a simplified expression for this probability here can be expressed in this form. So AK squared plus BK plus C, where A, B, and C are all just constants to be found, right? 4 marks then for the final part of this question here. Now, if you've already attempted then our set A predicted paper 3, you'll see in a question that is very, very similar to this one here, right? Now, what I did probably forget to mention here, really, if we're being precise, is x1 and x2 is this distribution here, where they are identical and independent of each other, right? So x1 is just this here, and the same is true for x2, right? So what I need to think about here then is the possible pairs, right? So what I want here is the possible pairs where the sum will give us 10. So what do I mean by that then? Well, for example here, if x1 is 3 and x2 is 7, then they sum to give us 10, right? So one possible pair here would be 3, 7. Another possible pair here would be 5 and 5, right? 5 plus 5 also gives us 10. We've got 5, 5 there. And then finally here, 7 and 3, right? So if x1 is 7 and x2 is 3, then they also sum to give us 10. So 7 and 3 there. Perfect. Okay. So therefore then, the probability here that x1 plus x2 here is equal to 10, that is equal to these products here, right? So for example then, for 3, 7 here, That's this probability times this probability here, right? So 0.6 minus 2k times 0.4 minus k. But just notice here then, that will also be the same for 7, 3, right? The order of multiplication doesn't matter. The result is still the same. So I've got two lots then of that product. So two lots here of 0.6 minus 2k times then 0.4 minus k. So 0.4 minus k there, like so. And what I've also got here then is the probability for 5, right? So that's 3k times by itself again. So 3k times 3k, which is just simply 3k all squared, which would just give us 9k squared, but I'll just show my working first before I actually evaluate anything. So for this bit here, we'll keep the 2 on the outside for now. So 0.6 times 0.4, that is 0.24. 0.24 there. 0.6 times minus k, so that's minus 0.6k. Minus 2k times 0.4, so that's minus 0.8k. So altogether then, once you simplify, we've got minus 1.4k. Yep, it's minus 1.4k there. Perfect. And then minus 2k times minus k, that is plus 2k squared. So obviously, just be careful with your signs, right? It is easy to trip up there, like so. And then 3k times by itself again, as I've already mentioned, that is 9k squared. Okay, like so. So now let's just multiply by the 2 here on the outside. So 2 times 0.24, that is 0.48. We've then got 2 times minus 1.4k, so that's minus 2.8k. Like so. And then 2 times 2, I get 4k squared. Like that. Don't forget the 9k squared at the very end here. Like so. And therefore then, if we simplify here, what do we get? So 9k squared plus 4k squared, that's 13k squared. So I've got 13k squared there. I've got a minus 2.8k. There's nothing else that we can do with that, so it's just simply minus 2.8k, right? So minus 2.8k there. And then finally here, 0.48. Again, I can't do anything with that, so it's just simply 0.48. Okay. And there we go then. So to finish with here, let's just state the values of A, B, and C here. So for A then, that's 13. For B, that is minus 2.8. So minus 2.8 there, like so. And then for C here, that is 0.48. Like so, okay? So there we go then, right? As you can see here, we've got it in the correct form. We've identified the values of A, B, and C. And there we go, bosh, question done. So that gives us the solution there to question 5. And now for the final question then of the stats section here of this applied paper, we have question 6, which is on probability, right? So what I've got here then is 2 events, A and B, which are mutually exclusive. We're also given here that the probability of B is equal to Q, which cannot be equal to 0. And the probability of A then is equal to 4 lots of the probability of B. So for the first part here then, A part 1, just want to draw a Venn diagram to illustrate this problem. All right, so let's just do this right at the very top here. Part A, right? So A part 1. Now let's just think about this logically here, right? Because the probability of B is Q. What I also know here is the probability of A is 4 lots of the probability of B, right? So what that means here then is the probability of A, let's just write this at the top. The probability of A then is 4 lots of the probability of B. So 4 lots of the probability of B. And the probability of B is Q, so that's 4Q there, right? So if we just draw this here as a Venn diagram, obviously the key point here is the events A and B are mutually exclusive. So there's no overlap or there's no intersection then between those two events. That's the key point here. So if we just draw a Venn diagram here, and by the way, it doesn't need to be a masterpiece, something like this here. And once I actually draw it anyway, will suffice. So we'll have 2 events, A and B. So that there will be A, and then this here will be B. Something like that, right? I've got A and B, like so. As I've already noted here, the probability of A is 4Q. So I'll drop that in the circle, like so. And then for the probability of B here, that's just simply Q, right? And we get the following. So nice and easy there for A part 1. Now for A part 2 then, a nice follow on here. It just says find the possible values of the probability of B. So what you should be aware of here then is the probability of A plus the probability of B here. That must be less or equal to 1, right? So let's just make a note here. The probability of A plus then the probability of B here, that must be less than or equal to 1. Well, I know both of these probabilities, right? The probability of A is 4Q. So 4Q. The probability of B is Q. So 4Q plus Q must be less than or equal to 1, like so. Simplify the left-hand side here. So 5Q is less than or equal to 1. And therefore then, Q must be less than or equal to a fifth, right? 1 over 5 there, okay? But just be careful here because what else do we know here? Well, I also know then that the probability of B here is equal to Q, but that cannot be equal to 0. So once I give the possible values of the probability of B here, we do need to be slightly careful because it can't be equal to 0, right? So in that case then, what we get here is the probability of B then is between, so it's between 0, but that's straight, it's because it cannot be equal to 0, and 1 over 5, but it can be equal to 1 over 5 there. So we make sure that we use the correct inequality, and there we go. I'll highlight this here, just to show then that this here is a solution to A part 2, okay? And there we go then, so that's the solution to 6 part A. Now I've got part B here to finish with, which again has 2 different parts. But the first part here is just 1 mark, so I'm not really expecting too much work. The final part is 6 marks, so that's probably going to take a little bit more time to get through that, right? Well, let's just start with B part 1 then. So B part 1 here. So what I've got here now is 2 events C and D, and they're such that the probability of C given D is equal to 2 lots of the probability of C. The probability of C cannot be equal to 0. So for the first part here then, we just need to determine whether the events C and D could be independent events. Now you should be aware here then that if C and D are independent, so if C and D are independent, then the probability of C given the event D here, that is just simply, I can't speak, that is just simply equal to the probability then of C, like so, okay? Now, that gives us a bit of a problem here because what we're told here then is the probability of C cannot be equal to 0, okay? Now, why is that a problem then? Well, what we're told here is the probability of C given D is 2 lots of the probability of C. So basically, these are both conditional on D, right? So the probability of C is conditional on D. Same here. So that's 2 lots of probability of C. This is equal to the probability of C for independence. Just make a note here for independence. So what I can do here then is set the probability of C equal to 2 lots of the probability of C, right? So I get the probability of C is equal to 2 lots of the probability of C. However, this equation here only holds if the probability of C is equal to 0, right? But since the probability of C cannot be equal to 0, this does not hold. Okay, so this does not hold. This does not hold. And what does that mean then? Well, hopefully it's obvious that this means then that the events C and D are not independent events. Okay, so therefore C and D are not independent. So independent, there we go. Perfect. Okay, so that's the solution to B part 1. Now, B part 2 does take a little bit more room. So what I will quickly do here is just clear the screen. Let's do that. Get rid of all that. And let's continue then with B part 2. So for B part 2 then, what do we want to do here? Well, I'm also given these 2 points here. Hopefully you can just about read these. So the probability of C intersection D is a third of the probability of C. And then the probability then of not C intersection not D is equal to 7 over 10. what we want to do here then is just find the probability of C, showing you're working clearly, which you should just be doing anyway. You shouldn't need the exam paper to tell you to do that, right? But where do we go from here? So B part 2 then, for 6 marks, right? It's going to take definitely a little bit more working for B part 2. I'm kind of just doing this off the cuff here, so there might be a slightly nicer way to do this. As I said, I'm just kind of doing this as it comes to me. So if you find a nice way to do it, then feel free to kind of share that in the comments. But let's just give it a go then. Okay. So what do we know here? So to begin with here then, I've got the intersection of C and D. And what I'm also going to use here then is the fact that the probability of C given D, so this is conditional probability, right? The formula for this then is the probability of C intersection D, probability of C intersection D, and that's all over then the probability of D, okay? So what I can do here then is replace this with 2 lots of the probability of C. There's 2 lots of the probability of C, like so. The probability then of C intersection D, that is a third, times the probability of C, so I can also replace that as well. That's a third times the probability of C. And then we divide this here then by the probability of D. Now, the probability of D here, I'm just going to leave that as it is, okay? So the probability of D there, like so, okay? Now, what we're also told here is the probability of C cannot be equal to 0. So that's important because what I can now do here is divide both sides by the probability of C, right? So divide both sides here by the probability of C. On the left-hand side, I just get left with 2. So 2 is equal to, so this one here will just cancel, right? Because I'm dividing by and the probability of C. It's the same as times by the reciprocal of it, so 1 over, it just cancels. So what I get then is 1 over 3 lots of the probability of D there, like so, okay? So where can I go from here? Well, let's just find the probability of D here then, because I can just rearrange here and make the probability of D the subject, right? So just times both sides by 3. So 1 over the probability of D is equal to 6, and therefore then the probability of D here is equal to the reciprocal of that. So 1 over 6, okay? What else do we also know here? So we're told then, this point here, that the probability of C, or sorry, not C, intersection not D, is equal to 7 over 10. So in that case, then the probability of C union D would be the complement of that. So 1 minus 7 over 10, okay? So if the probability then of not C intersection not D is equal to 7 over 10, then as we've just said here, the probability of C union D will be the complement. There we go. English is hard. It'll be the complement then of this here. So that's going to be 1 minus 7 over 10, which is just simply 3 over 10, right? Like so. Okay. And at this point here, we're pretty much there now, right? So what I'm going to do here is just use the addition formula. So using addition formula, hopefully I should have just about enough room here. It's looking pretty tight. So using addition formula. So just in case you forgot it here, the addition formula then will be, so it's going to be the probability of C union D, and that is equal to the probability of C plus the probability of D. That is supposed to be a P, by the way, apologies, minus then the probability of C intersection D, okay? So we know this here, that's 3 over 10, as we've just evaluated, right? So that's 3 over 10, and that is equal to, so probability of C, what was that? So we don't know what that is, right? That's what we're looking to find. So that's the probability of C. Leave that as it is. The probability of D, we evaluated that before. It was 1 over 6. So 1 over 6. There's too many probabilities, right? It's hard to keep track. But there we go. So 1 over 6 minus this intersection here. So the probability of C intersection D, that is a third times the probability of C, right? So minus then 1 over 3 times the probability of C. Does that look good up to now? I can't spot any silly mistakes, so I think that's okay. Let's just continue from here then. So the probability of C minus a third of the probability of C, so that's 3 over 3, minus 1 over 3, so that's 2 over 3 times the probability of C. This is getting pretty close, so 2 over 3 times the probability of C is equal to, so that's 3 over 10 minus 1 over 6 there, which gives us 2 over 15. I get 2 over 15 there, okay? And what I want here then is just the probability of C, right? So therefore then, the probability of C here is equal to, so it's going to be 2 over 15 times by 3 over 2, right? So 2 over 15 times 3 over 2, which if we evaluate here, that's going to give us 6 over 30, which is 1 over 5, right? And there we go then. So the probability of C here is just simply 1 over 5, okay? And there we go then. So as you can see, the final part of this question here, is definitely a lot more involved. And there's a lot of different probabilities going on with that part of the question. It is very easy to kind of trip up and get kind of jumbled up as you go through it. So just take your time with these types of questions. Just make sure that you're being, quite clear with your working, more for your sake than anything as well, just so you don't make any silly mistakes. Okay. But there we go then. Hopefully you did get the same as me. And as I said, right, I'm kind of just doing this as I go. If you spot a better way to do it, then feel free to share that. But I think that's probably a pretty decent way to do it. Okay. But there we go then. So that gives us the solution here to question 6. And that concludes the stats part of the paper here. So that's the first 50%. So to finish with them, right? Deep breath. We've got the final 50%, which is on mechanics, which isn't my favorite, but it is what it is, right? So there we go then. That gives us the solution here to question 6. Now for question 7, then we have the first of the mechanics problems for this paper, right? So we've completed the first 50% of the paper, which was all stats, right? And now the remaining 50% here is mechanics. Now, if you're like me, you don't particularly enjoy mechanics, and I feel your pain, but it is still half the paper. So let's just give it our best shot, and let's just see how we get on here. So question 7 then. What we're told here is at time t seconds, a particle P has this position vector here, so r meters with respect to a fixed origin O, where r is given as the following. So for the first part then of this question here, so part A, it just says then find the velocity of P when t is equal to pi over 2. So don't forget then, we're starting with the position vector here, or the displacement. So r, if you move down then, you've got v here, and then if you go down one more, you've got a. You can also think of r here as s, the displacement. So going down here, so to go from the displacement or the position vector here to the velocity vector, I would differentiate with respect to time t. And then same again here. If you've got the velocity vector and you want the acceleration vector, then again, we differentiate with respect to time t. I didn't leave myself a lot of room here. So that is d by dt. And then it doesn't really kind of apply to this question here, but let's just kind of discuss it anyway. If you're going backwards then, so if you've got the acceleration vector and you want the velocity vector, and going backwards, we integrate here with respect to time t. Okay, so integrate there with respect to time t. Now, we've got the position vector here, r. I want the velocity vector because I want to find the velocity of p when t is equal to pi over 2, right? So let's just differentiate this expression here with respect to time t. So as we already mentioned then, the velocity vector v here is equal to d by dt of then the position vector r. Okay. We just do this underneath here. The velocity vector is going to be, so just differentiate term by term here, right? Nice and straightforward. So the 3 sine 2ti, that just differentiates to give us 6 cos 2ti. So we get 6 cos 2ti there, like so. And then for this term here, so 3 cos 2tj, that will differentiate to give us, so we get minus 6 then, so minus 6 sine 2tj. Minus 6 sine 2tj, like so. Okay, so this here then is the velocity vector for this problem. But what we want here is the velocity of p when t is equal to pi over 2, right? Now, for each of these trig expressions here, or these trig functions here, the argument is 2t. So if t is pi over 2, then 2t is just simply pi, right? So what I get here, when t is equal to pi over 2, what we get then is, so the velocity vector here is going to be, so it's 6 cos pi I. So 6 cos pi I there, like so, minus 6 sine. So minus 6 sine, again, pi here, j, like so, okay? Well, sine of pi is 0, cos of pi here is minus 1, right? So what I get here is 6 times minus 1, so that's minus 6 there. So what I get here then is the velocity vector is equal to, so it's going to be minus 6i meters per second. So minus 6i meters per second there, like so. So ms to the minus 1 there. And there we go. So for 5 marks, I think that's really quite straightforward. Even if you don't enjoy mechanics, I don't think that should be too bad, right? So that's the first 5 marks there in the bag. Now for the final part of this question here then, so part B, again, relatively straightforward, I do think. Probably a little bit more challenging than part A, but even so, for another 4 marks here, this really isn't too bad, right? So for part B then, it says, show that the magnitude of the acceleration of P is constant. So for the acceleration vector here, so that's the acceleration vector here, that is going to be the derivative then, with respect to time t here, of the velocity vector, right? So d by dt of the velocity vector, like so, okay? So let's just do this underneath then. So therefore here, the acceleration vector A is equal to, so again, just differentiate term by term here. We're differentiating this expression here. Oops, I knocked my microphone. Apologies if you could hear that. So just go term by term here. So the 6 cos 2ti, that will differentiate to give me minus 12 sine 2ti. So minus 12 sine 2ti there, like so. And then for the minus 6 sine 2tj, that will differentiate to give me minus 12 cos 2tj. Okay, so obviously just be careful with the signs here. And that's the only real place that you can trip up here with this question. So minus 12 cos 2tj, like so. Okay. Now, what we want to show here is that the magnitude of the acceleration of P is constant. So let's just consider here then the magnitude of the acceleration vector here. If we do that underneath then, the magnitude here of the acceleration vector A, that's going to be equal to then. So don't forget, this is just simply an application of Pythagoras. So what I've got here is the square root then of, so what we've got here is minus 12 sine 2t all squared. So minus 12 sine 2t, that's all squared, plus then, and we just square this term here, so minus 12 cos 2t all squared as well, okay? So let's just simplify this here then. These are both negative, so once you square those, they obviously become positive, right? So what I'm going to get here is the square root then of, so I get 144 sine squared 2t, 144 sine squared 2t, like so. So that's the first term squared. Doing the same here then for the second term. What do we get? So we get 144 again. 144. This will now be cos squared. So 144 cos squared 2t, right? Just like that. Now, at this point here, that isn't showing us that it's going to be constant here. We do need to do a little bit of manipulation to then show that the magnitude of the acceleration of P here is constant, right? So what I can do here is play the 144 as a factor, right? It's a common factor here for these two terms. So I've got the square root then of 144 times then, so I've got sine squared 2t plus cos squared 2t. So sine squared 2t plus then cos squared 2t. Let me just extend this here, like so. And hopefully, at this point here now, you can see why the acceleration, or the magnitude of the acceleration of p here, is constant, because this part here, so sine squared 2t plus cos squared 2t, that's just 1, right? Just our basic A-level maths trig identities here from year 1 material. Sine squared x plus cos squared x is equal to 1. So what I've got here is square root then of 144, which is just simply 12, right? So therefore then, why does my pen keep doing that? Therefore then, the magnitude of the acceleration vector here is equal to, so it's going to be 12 meters per second squared. 12 meters per second squared there. And as we can see then, it doesn't depend on t, right? So therefore then, it is constant and is therefore constant. Okay. And there we go then. So as I said, right, I think for 9 marks in total for that question, that's really not too bad. Okay. So there we go then. That gives us the solution here to question 7. Now, moving on to the next question here then, question 8. What we've got here is a question on forces, right? So we've got a rough plane here that's inclined to the horizontal at an angle theta, where tan theta is equal to 5/12. We've then got a particle of mass m here that's placed on the plane and projected down a line of greatest slope of the plane. The coefficient of friction between the particle and the plane is mu, and the particle moves down the plane with a constant deceleration of g/13 or 1/13g, whichever you prefer, right? So for part A then, the first part of this question here, what we want to do is find the value of mu, right? The coefficient of friction here between the particle and the plane. Now, as always for these types of problems here, I would definitely recommend just drawing a quick diagram. It doesn't need to be a masterpiece. You're not expected to be Picasso or anything like that, right? Just a very quick force diagram here will help us answer this question a whole lot easier. So we'll start with the inclined plane here. So I've got the horizontal, which is supposed to be a straight line, but I can't do that. We've then got the inclined plane, something like that. Okay. We've got the angle of inclination here, which is theta. So that is theta. I'll just draw it underneath here. Just so I can kind of add the relevant forces to my diagram without everything being all squished. So that's fine. We've then got the particle here, which you can draw as a circle or a box, whatever you want here. I'll just draw it as a circle. Something like this. Okay, so this here is our particle. So we now need to add the relevant forces here. So we'll have a normal reaction between the inclined plane and the particle, right? That goes up like so. And I'll label that here as R. Okay, so that's the normal reaction there. What else do we have here? So we've got the weight force acting vertically downwards. It's going to look like that, right? So the mass here is M. So the weight force is just simply mg. Okay. And for this force here, we should split that into components. So we've got this component here acting down like that. And this component here acting down the plane, like so. Okay, so this gives us a right angle triangle with a little bit of basic trigonometry here. What we get then is, so this component here, that's going to be mg cos theta. So the angle here is just theta as well. So that's going to be mg cos theta. And then for this component here, you might have guessed it by now, it's going to be mg sine theta. Okay. And do I need anything else here? Yes, I also need to account for friction, right? Because it's been projected down a line of greatest slope of the plane, so it moves down the plane. So friction opposes motion, right? And friction will act up the plane. Okay. We've got friction up the plane here, and we'll label that as mu r, like so. Okay. You could also label it as F as well. Either's fine, but I'll keep it like that for now. So to begin with here, for the value of mu, what can I do then? Well, what I can do here is resolve perpendicular to the plane, right? And we can solve for r here, okay? Or get an expression for r here, basically, because we don't know m, so I can't get it as a numerical value, but we can get it as some expression here. So resolving perpendicular to the plane then, I'll take up as positive here. So r is going up, so that's positive. So what I get here is r. There's no acceleration in this case here, so it's just going to be the forces acting up being equal to the forces acting down, right? So r here is equal to this component of mg cos theta. So mg cos theta, like so, okay? So that's all well and good. What I also know here as well then is because f, so f here is equal to mu r, as we've noted here then on our diagram, then this is going to be, so it's going to be mu times mg cos theta, right? So it's going to be mu mg cos theta, like so. So that's all well and good up to now. And at this point here, let's now resolve parallel to the plane, okay? And what I'll do here is I'll take down the plane as positive, but you could also do the opposite here and take up the plane as positive. It doesn't really matter, right? As long as you do everything correctly here, everything should still work out correctly. So let's now resolve parallel to the plane here, taking down the plane as positive then. So what do we get here? So we do have acceleration here. So it accelerates down the plane, right? So a meters per second squared there. So we do need to account for Newton's second law here, right? F equals ma. That is relevant now for resolving parallel to the plane. So what do I get here then? So acting down the plane, I've got mg sine theta. So mg sine theta. There's no more forces acting down the plane here, so that's all well and good. What forces are acting up the plane here? Well, that's just friction, right? Mu r, which is this here. So that's going in the opposite direction. So we take the negative of that. So minus mu mg cos theta, like so, okay? And this here then is equal to the mass times the acceleration. Now, what we know here then is the mass is m. So leave that as m here, like so. I can't do anything with that, right? But we can times it by the acceleration here. So this is a constant deceleration of 1 over 13g, or g over 13, whichever you prefer. So we'll take that as negative here. That's going to be minus 1 over 13 g there, like so, okay? So what can we do here then? Well, we can divide both sides by mg, right? So we can divide by mg on both sides here. That m and that g just cancel. So what I get left with here then is, so we've got sine theta. So sine theta minus cos theta is equal to minus 1 over 13. That all looks correct. I can't spot, oops, I have forgot my mu there. So I was about to say I haven't made any silly mistakes, but that is an impossible challenge for me. So minus mu cos theta, there we go. Nearly made a silly mistake. So that's all good now. So because we know then that tan theta here, so tan theta is equal to 5 over 12, right? By some basic trigonometry here then, we've got a Pythagorean triple essentially, right? Of 5, 12, 13 here. Okay, so if tan theta is equal to 5 over 12, what I also know here then is sine theta is going to be 5 over 13. That's 5 over 13. And cos theta, so cos theta here is going to be 12 over 13, right? So sine theta is 5 over 13. So I've got 5 over 13 there. Minus mu times cos theta. So minus mu then times cos theta. So cos theta is 12 over 13. So I get minus 12 over 13 mu there. And that is equal to minus 1 over 13. Okay? So to make my life a little bit easier here, right, let's just times through by 13. It should just simplify the calculations here. So I get 5 minus 12 mu is equal to minus 1. I'm going to add 12 mu to both sides here and add 1 to both sides. So I get 12 mu is equal to 6, like so. And then if we just want mu here, right, the coefficient of friction here, just divide both sides by 12. And therefore mu here is 6 over 12, which is just simply 1 over 2, right, or 0.5, whichever your preference is, okay? And there we go then. So we find the value of mu there, giving us a solution to or part A here of question A. So lovely jubbly, that gives us the solution there to the first part. But we're not done here because we also have part B as well. So let's just do that over here on the left-hand side. So what we're told here is the particle comes to rest at the point B on the plane, right? So you can imagine here, the particle is projected down the plane, and at some point here, it kind of just stops. Let's just say at this point here, okay? Now, we need to determine then whether the particle will remain at B, carefully justifying our answer. So will it remain at this point here, or will it continue then to slide down the plane? Well, the particle here will remain if friction is large enough to prevent sliding, right? If the friction isn't large enough to prevent sliding, then it'll just continue to move down the plane. But if friction is large enough, then it will remain at B, right? So what we know here then is F max. So the maximum frictional value here is equal to mu R, okay? Now, we know then, going down the plane here, we've got mg sine theta, right? It's this component here. Let me make a quick note then. So down the plane here, we have mg sine theta. As we said before, it's just this component here, right? So we know sine theta, that's 5 over 13. So what I've got here is 5 over 13 mg, okay, like so. Now, going back to F max here, as we said before, that's mu R, right? So F max here, as we said before, is mu R. Now, from the previous part of the question, then we just deduced the value of mu, right? The coefficient of friction here. That's 1 over 2. So I've got 1 over 2 here times R. And as we evaluated before then, R here is just simply mg cos theta. So what I've got here is a half mg cos theta. So that is 1 over 2 times then, so it's mg, and cos theta is 12 over 13. So I've got 1 over 2 times then 12 over 13 mg. So what does that simplify to give us then? So 1 over 2 times 12 over 13, that's going to be 6 over 13. I get 6 over 13 mg. Apologies, by the way, my handwriting is disgusting, but that'll do. So what can we basically say here then? Well, what we can see here is F max, the largest frictional force here, is 6 over 13 mg. And the force going down the plane here, that's 5 over 13 mg. So what we can see here then is friction is going to be large enough to stop the particle sliding down the plane, right? Because what I've got here then is 6 over 13 mg, which is straight larger than 5 over 13 mg, right? So 5 over 13 mg, like so. So to finish with here then, let's just give a quick conclusion, just to show the examiner that we actually understand what's going on, rather than just kind of doing all of this work in here. So therefore then, friction is large enough. The friction is large enough here to stop the particle, moving down the plane or sliding down the plane, whichever you prefer here. Sliding down the plane. And therefore then, remains at B. Beautiful stuff, okay? And there we go then. So I think the key thing with this question here, and I would definitely recommend doing this for any similar type question here, on your exam is to just draw a force diagram here. As you can see, it took me a minute or two at max here, and it just kind of helps to illustrate the problem at hand. It makes it a lot easier to see then what you're actually dealing with for the problem, right? Trying to attempt a problem such as this one here without a diagram, it's not impossible, but you're just making life a lot harder than it needs to be, right? So draw a quick diagram here, as we've done then, and then just continue with the question, right? Well, there we go then. So hopefully not too bad there for question 8, and that gives us the solution to this question. Now moving on to the next question here then, question 9. What we've got here is a football that's kicked from a point A with a speed of 36 meters per second at an angle of elevation of 30 degrees. Now, on its downward flight here, the ball hits the crossbar of a goal at a height of 2.4 meters above the level of A. So for this question here, then we want to find the following 3 things here, given all our answers to 2 significant figures. So for question 9 then, part A, let's just start here, right at the very top, right? Now again, similar to the previous question here, what I would just do then to begin with here is to just draw a quick diagram. And again, it doesn't need to be a masterpiece or anything like that. All we want to do then is just essentially visualize this problem, okay? Because what we've got here is a projectiles problem. So if I just draw my diagram right here at the top, this is my horizontal, like so. I would have the vertical here. I'll add it on for now, like so, okay? We've got the ball here that's kicked, so we'll just take that as the point A, okay? So we've got the path of the motion here, which would look, say, something like that, okay? And at this point here, so this is the point then where it hits the crossbar of a goal. Now, to actually draw a goal and a crossbar in a 2D coordinate system, that is rather challenging. It's probably the most challenging part of this question here. So imagine you've got your crossbar. So I don't know, this here is supposed to be my goal. That's the crossbar. You get what I mean. I'm rubbish at art. So this here is the problem that we're dealing with. Okay. So what I can do here is essentially just draw a rectangle triangle, right? Because you've got your initial velocity like so, okay? So I've got our right angle triangle here. If I just draw it as I've just kind of denoted them, we'll have the following. Again, this is a right angle triangle. This here is the angle of elevation, which as we're told here is 30 degrees. So I'll add that to my diagram as well. As you can see, my art skills do leave much to be desired, but it will do for this problem here. So that's 30 degrees. So what I've got here is 2 components, right? I've got the horizontal component here, like so. What I'll actually do is I'll just do these in 2 different colors, just so it's a little bit easier to see. Got the horizontal component here, like so. And we've also got the vertical component. And that goes up like so, okay? Let's just start with the horizontal component here. So for the horizontal component here, that's going to be u cos alpha. So u here is the initial speed, which is 36 meters per second. So all we're going to get here then is 36 cos of the angle of elevation, which in this case here is 30 degrees, right? So what I get here is 36 cos of 30 degrees. Perfect. Okay. And then for the vertical component here, let's do that in the correct color as well. That will be pretty similar then. You might have guessed it by now. That's going to be 36 sine of 30 degrees. Like so. Okay. So let's start putting this all together here then. So the horizontal component here, that's ux, right? So what I've got here is ux. That's the initial velocity in the horizontal sense. And I've also got uy. So uy here is the initial velocity in the vertical sense. So ux here, as I've already kind of noted here then, is 36 cos of 30 degrees. So 36 cos of 30 degrees, like so. And then for uy here, that's going to be this component, right, of 36 sine of 30 degrees. So 36 sine of 30 degrees there, okay? So sine of 30 degrees is a half, so 36 times a half is 18. So you can just write that as 18 there. It would be 18 meters per second, like so. And cos 30, I'm just going to keep it as this for now, right? Because it's not something quite as neat as this here. So I'm just going to keep it as 36 cos of 30 degrees. Okay. Now, for the first part of this question here, then, what we're actually looking to find is the time taken by the ball to reach its greatest height above A. Now, you should be aware then, and this is pretty common with the, the constant acceleration formulae questions, and we're looking at something like a projectile being thrown upwards, right? And the greatest height occurs then when the velocity is 0. And in this case here, right, because we're considering the velocity as two different components, the horizontal and the vertical velocity, then what we require here is the vertical velocity to be 0. Okay, so at greatest height then, so at its greatest height here, at greatest height, the vertical velocity then is 0. Okay, so Vy here will be equal to 0. So what we're going to use here then is just some basic suvat, right? Because we can use then, so just use here, V is equal to U plus AT, right? Because the acceleration A here, that's going to be G or minus G, depending on what you take as positive or negative. U is our initial velocity, and V is just 0, right? So we want to find T, and we can just simply find that then by using this here. So V then, as I've already kind of denoted, is just going to simply be 0. Now for U, just be careful here that you do use the correct component. What we're going to use here is the vertical initial velocity, right? So Uy here, which is 36 sine of 30 degrees, which is just simply 18. Okay, so we get 18 plus then 18. Now, what I'm doing here is I'm resolving taking up as positive here, taking up as positive here. So A will be minus G here. So just be very, very careful for that. I'm going to get minus G times T. So I get minus 9.8 T there, right? Because G here, we take that to be 9.8 unless told otherwise. So minus 9.8 T there, okay? And all we simply need to do here then is just solve for T, right? So what I get here is 9.8 T is equal to 18. And therefore then, just divide both sides by 9.8. So T is equal to 18 all over 9.8. Throw this here then into your calculator. And if you do this correctly then, what we get here is 1.84. So to 2 SF here, that would just simply be 1.8 seconds there. Okay. And there we go then. So that gives us the solution to part A there. So that's the first 3 marks in the bag. Now for part B then, what do we want to find here? So we want to find the time taken by the ball to travel from A to the crossbar. So from this point here to this point here, what is that time to get to there, right? So to do this here then, we're going to use suvat again. And to begin with here, let's just resolve vertically. So I'm going to use this, or I'm going to write this as the following. It just makes it a little bit easier for me here to see what we're doing. And as we said before then, we'll resolve vertically here, taking upwards as positive. Similar to the previous part, right? So for S here, what is the displacement then if we're resolving vertically here? So that's going to be 2.4, because as we're told here, it has a height of 2.4 meters above the level of A. So S is 2.4. For U here, again, just make sure that you use the correct component here. It'll either be 36 cos 30 degrees or 36 sine 30 degrees. But again, because we're resolving vertically here, we use Uy. Okay, so that's just going to be 18 here. It's just simply 36 sine 30, which is 18. That's 18. For V, nothing relevant there. For A, that's minus G, so minus 9.8. And again, what we're looking for here is T, right? The time taken by the ball to travel from A to the crossbar. So I'll put a question mark there, okay? So based on the information that we've got here then, what formula will we use, right? What trusty old suvat equation are we going to pull out here? So we're going to use then S is equal to, so it's UT plus a half AP squared, like so, okay? And we've got everything that we need here, right? S is 2.4. So what I've got here is 2.4 is equal to, so U times T. U is 18, T we don't know what that is, so it's 18T there, like so. Plus then a half times A, which is minus 9.8, times minus 9.8, and that's T squared, so it's going to be a half times minus 9.8 T squared, okay? And what we want to do here then is just solve for T. Now, what you might have recognized straight away is we're going to get a quadratic equation in terms of T. So there's a very, very good chance here that when we solve this, we're going to get two solutions for T. So we'll see how we deal with that in just a moment. So for now, let's just simplify this here. I've got 2.4 is equal to 18T. A half times minus 9.8, that's minus 4.9. So I've got minus 4.9 T squared. Okay, so altogether here we have 4.9 T squared minus 18T plus 2.4 is equal to 0. Okay. And as we said before then, we now want to solve this quadratic equation, okay? You could have also just subtracted 2.4 from both sides here. That would have been absolutely fine as well. But either way, just throw this into your calculator. You don't need to solve this by hand. Don't do that. Just use the calculator, right? And if you do this correctly then, what we get here, as we said before, is two solutions for T. So what I get here is T is equal to 0.138, like so. Or T is equal to 3.54, okay? Now, why do I get two solutions here? Well, if you go back to the graph here, or our diagram then, and I'll do this we'll do it in green. What I'm looking for then is basically where the height is this, right? And as you can see, then we get this at 2 points. I've got this point here and this point here. So these two solutions for T here correspond to these two green points, right? This one here clearly being the smaller of the two values of T, so that's going to be 0.138, and then this one here would be 3.54. So clearly we choose the larger of these two values, right? So therefore then, and let's just make sure that we give this to two significant figures. I've given it to 3 here. So the time taken then, so therefore time taken is 3.5 seconds there. All right, seconds, why not? So the time taken is 3.5 seconds for the ball to travel from A to the crossbar there, okay? And there we go then. So that gives us the solution to part B. So we've got the final part of the question here, part C. What I don't want to do is just cram this into the bottom right corner here. I probably would have enough room, but rather than kind of cram it all in, what I'll quickly do then is just clear the screen and we can continue with part C. I'm just checking whether I need to keep anything. We will need the components here. So let's get rid of this for now. So I've kept these here on the screen, just so we've got these right. So on my diagram here, just so we can kind of reference that. So for part C here, what do we want to find then? So what I want to find here, again, given our answer to two significant figures, is the speed with which the ball hits the crossbar. Now, what we know here is that the horizontal velocity will not change because there's no horizontal acceleration, okay? So I can write here that v subscript x, the final velocity for the horizontal component, or in a horizontal sense here, that would just simply be 36 cos of 30 degrees, okay? So we'll leave that as it is. Now, for the velocity in the vertical sense here, so it's going to be Vy, so the final velocity, so Vy here, that will change depending on the time taken, okay? So what we're going to use here is V is equal to U plus AT, right? So now use V is equal to U plus AT, right? So V here, that's what we want to find. That's going to be Vy actually. So Vy then is equal to U. So U here is just simply 18. It's 36 sine 30 degrees. So it's going to be 18. And I'm taking up as positive here. I should really be defining that as I go. So 18 minus then 9.8 times T. Now T here is the value that we just found in part B. So T here, that was 3.5, right? It's going to be minus 9.8 times 3.5, like so. Okay. And if we evaluate this here then, what do we get? So 18 minus this product here, what we get then is minus 16.7 meters per second there. Okay. So for the final speed here then, it's just a simple application of Pythagoras, right? So therefore then, for the final speed here, that, as we just said, is a simple application of Pythagoras. We do the square root here then of, that is the worst square root symbol ever, but it'll do. So it's going to be then 36 cos of 30 degrees. So 36 cos of 30 degrees. We square that, and then we add here the square of Vy, right? So minus 16.7 squared. So minus 16.7 squared, like so. So obviously just throw this here into your calculator. And if you do this correctly then, what we get here is 35.4 there, okay? So this here then is the final speed. So let's not forget the units as well, right? So meters per second there. So the speed with which the ball hits the crossbar to two significant figures here is going to be 35 meters per second. So the speed is 35 meters per second there. Bosh, good stuff, right? So there we go then. It's quite a classic projectiles question here. 3 individual parts where, it's testing those key, ideas behind projectiles using SUVAT, drawing your diagram here. Again, you don't have to draw a diagram, but I would definitely recommend it for a problem such as this one. Okay. Well, there we go then. So that gives us the solution here to question 9. Now for the next question here then, question 10, we have one of those classic ladder problems that all students just absolutely love then for the mechanics part of the paper, right? I'm also in that camp then that I absolutely hate these questions. They're never particularly fun. They are just painful. But anyway, let's just try and work through question 10 here. As we can see, there is a little bit of waffle here to quickly read through. So let's just do that then. And then we can attempt part A here for the first 6 marks of this question. So what we've got here is a ladder AB, which has a length of 8 meters and a mass of 25 kg. The ladder rests in equilibrium at 60 degrees to the horizontal, with the end A on rough horizontal ground and the end B against a smooth vertical wall. Now, a woman of mass 60 kg stands on the ladder at the point C, where AC is 3 meters, and the ladder remains in equilibrium. Now, the ladder is modeled as a uniform rod in a vertical plane perpendicular to the wall. And the woman is also modeled as a particle. So, for part A then, let's just set this up here. Right at the very top then, it just says, find the magnitude of the force exerted on the ladder by the ground. Absolutely classic, right? Now, most of the time they will give you a diagram with these problems, but very occasionally you won't get a diagram. Now, for this question, so question 10 and, just these kind of like general static rigid body questions, if you don't have a diagram, please just draw a diagram. It is absolutely essential for these types of questions. So I'll just start then by drawing a very quick diagram. As I've already said a few times in this video here, it doesn't need to be a masterpiece. But what we've got then is the horizontal ground. And then we've also got the wall here. So something like that would be absolutely fine. Okay. And then between the horizontal ground and the wall, we have a ladder, something like that. Okay. And that forms then a right angled triangle. Now there's 2 points to consider here. Well, there's 3 in total, but for now, 2 points. So I've got the point A here. That's A there. And I've got the point B here. So this is the wall. I'll draw kind of like dash lines against it just to indicate that that's the wall. And then this here is the ground. Now the ground then, as we're told somewhere in the question, I did read it somewhere. So it's a rough horizontal ground. So we'll need to account for friction. So if the ladder's going to move at some point, right, then it would move to the left here essentially, right? If that makes sense. So friction will oppose the motion and friction will go in this direction here. So that's F of friction. What we'll also have here is a normal reaction. So a normal reaction. Let's just label that as R, like so. And we'll have something similar then at B here. So a reaction at the wall between the ladder and the wall. So that goes out to the left, like so. Now, sometimes students prefer to label this as, for example, R1 and R2. That's absolutely fine. I normally just kind of label this as R and N, but again, it's completely up to you. It's just a preference thing. So I'm going to call this here then N, like so. What else do I need here? So I need the weight force then. So what I know here is the ladder is modeled as a uniform rod. So the center of mass then acts directly in the middle of the ladder. So the ladder has a length of 8 meters. So that's going to be halfway between then the ladder. So if it's 8 meters in total, that's going to be 4 meters, which is, I don't know, roughly there. Something like that. So that's going to be 25. So, well, sorry, the mass is 25 kg. So that's going to be 25 G acting vertically downwards. There we go. What does help for these problems here is if you draw a diagram that is slightly bigger. I'm not giving myself much to work with here, but it'll do. And also then, we know that a woman of mass 60 kg stands on the ladder at the point C where AC is 3 meters. So this point here is 4 meters along. So A to C then must be somewhere like this here. And that then is 60 G because the woman has a mass of 60 kg. So that is 60 G, like so. Okay. And I think at this point here, that is everything that we need. If I am missing anything, then I'll just drop it on a little bit later into the question. But for now, that should do. So let's just get started then with part A. So we want to find the magnitude of the force exerted on the ladder by the ground. So what I'm going to do here then is just start by taking moments about A. Okay. So taking moments about A here. So what will we get then? So let's just start with this point here, C, or going from A to C essentially. So what you need here is the perpendicular distance, right? For that, you can just use some basic trigonometry. I mean, the more of these questions you do, you'll get quite used to this concept then. So this length here for the hypotenuse, that's going to be 3. So that's 3 there, right? And this angle here, I didn't include it on the actual diagram, but that's 60 degrees. So what I know here then is the perpendicular distance here is going to be 3 cos of 60 degrees. So perp distance by basic trigonometry then, as we've just said, is going to be 3 cos of 60 degrees. 3 cos of 60 degrees there. Perfect. Okay. So what I've got here then is the mass, which is 60G, times by the perpendicular distance. So I get 60G times then 3 cos of 60 degrees. If you want to, because obviously these angles here, for example, cos of 60 degrees, it's going to give me something that's relatively nice to work with. Then you can evaluate these beforehand and then just kind of replace them at this point here. That's also fine. I'm just going to do it a little bit later on. So I get this here. We also need to account then for the mass here of the ladder. So that's 25G, and that distance will be 4 there. So the perpendicular distance then is going to be 4 cos of 60 degrees, right? Pretty similar to this one here. So that is, so that's 25G times by 4 cos of 60 degrees, like so. What I do wish here is that I gave myself a little bit more room. I've not got too much to work with here. And then finally, this will be equal to then So what I want to consider here then is at B. So for that, what I need then is the height here. That should be a straight line, straight arrow. You get what I mean? For the height then, that's going to be 8 sine of 60 degrees. Okay, so that's 8 sine of 60 degrees. I don't have enough room to really add it there. I should have kind of given myself a little bit more room to work with. But yeah, the height here is 8 sine of 60 degrees. So that's going to be 8 times root 3 over 2. So that's for root 3, right? So what I've got there is the perpendicular distance, which is 4 root 3, times by the magnitude here, which is n. So that is equal to then 4 root 3 n. Okay. Apologies, by the way, my presentation here isn't the neatest, but hopefully you can just about follow along then. Okay. And we get all of this here. So let's just quickly simplify then. So 3 cos of 60 degrees, that's going to give me 1.5. So I've got 60g. So 60g times 1.5. For cos of 60 degrees, that's 2. So I've got 25g. That's 25g times 2. And that then is equal to 4 root 3 n. I am regretting that I didn't give myself a little bit more room here, but hopefully you can just about follow along. So if you simplify this here then, what do I get? I've got 90 plus 50, so that's 140g. So I've got 140g is equal to 4 root 3. So 4 root 3 n, I should say, right? 4 root 3 n. Yes, there we go. And then finally, what I want here is just n, right? So if I just want n here, then I'm just going to divide both sides by 4 root 3. So therefore n here, and I should italicize this here, and you'll see why in just a moment. Maybe choosing n wasn't the best idea. It doesn't matter for now. So n then is equal to 140g all over 4 root 3. Throw this here then into your calculator. And what this gives us here then is 198. Now this is a force, so the units then are newtons. Newtons we don't italicize, so you would just keep it like that. Which is why I said using n here for this force probably wasn't the best idea, but never mind, we'll roll with it. What I also know here as well then is R is going to be equal to 85g. Yeah, because that there is 60g. So R here, that's going to be equal to forces acting up being equal to forces acting down. I've got 25g and 60g acting downwards, so R is 85g there as well. And what I can also see here is that if you resolve horizontally here, F is equal to N. So F is equal to N, okay? So what that means then is that F is 198 newtons, okay? So we're pretty much there now. So the force exerted, on the ground is, so what is that calculation? Well, it's going to be then the square root here of, so it's going to be 85g squared, 85g squared, like so, and then it's going to be 198 squared as well, right? Like so. Roll both of these then into your calculator, obviously square both of these and then take the square root of the sum. And if we do this correctly here, then what we get is 856 newtons there, okay? And there we have it then. So that gives us the solution to part A. Hopefully that wasn't too bad, but I do know that these types of problems, so these ladder problems, these classic problems do always cause issues. So as always, if you did struggle with that, just leave us a comment down below and I will try my best to help explain anything that I maybe didn't explain too good with the question here. But anyway, I'm just waffling. Let's just continue with part B then. So let's just do that underneath here. So what we're told here then is the woman climbs further up the ladder. So you can imagine she kind of just moves further up the ladder here. And when she's at the point D on the ladder is about to slip. So, oh no, she's going to fall, right? So given that the coefficient of friction between the ladder and the ground is 0.35, what we want to do here then is just find the distance AD. So if you ever see some kind of problem where it's going about the ladder slipping, then we're going to use F equals mu r here, right? It's limiting. So F here is equal to mu r, okay? Now, I know what mu is because we're told that in the question. So this here, that is mu. And then for r here, so as we established in the previous part of the question, r is equal to 85g, right? So what I've got here then is 0.35 times then r here, which is 85g, okay? So that is 85g there, like so. And if we evaluate that here, then what do we get? So I get 291.55 there. So 291.55. Okay, perfect. Now, horizontal equilibrium here tells us then that n is equal to f, right? So we know then that n here is equal to f, okay? So if n is equal to f here, then because f is 291.55, then what that means here is that n is 291.55 there, okay? What I'm also going to do here then is because we know she moves some point up the ladder here to some point D, right? Now, we don't know what that distance is. That's what we're going to find for part B. But for now, let's just call that distance then. So imagine she moves up here from A to some point in the ladder here. Let's just call that D. I'm going to call this distance here X. Okay, so that's X meters there. Okay. So if AD is equal to X here, then the horizontal distance, so horizontal distance here, horizontal distance. So the horizontal distance here will be equal to X cos of 60 degrees, right? It's going to be X cos of 60 degrees, similar to what we did in the previous part here, when we had the free cos 60 degrees and the forward cos of 60 degrees. So I get X cos of 60 degrees, which is just the same then as X over 2, right? Like so. So now let's just take moments at A here, and we can kind of just use the answer from part A to help us do this. So taking moments about A here, what would I get then? So I'm going to get 25g times by 2 here, as we did before. So 25g times by 2. I'm going to try to use my answer from the previous part just to help kind of speed this up here. So 25g times 2, as we did previously. So that's a 25g for work cos of 60 degrees. That's all well and good. And now, so what was originally free cos of 60 degrees here, that now becomes this here, right? Because she's moved further up the ladder. Okay, so she's not at C anymore. She's at the point D. So that's going to be then 60g, so plus 60g times X over 2. Like so. Okay. And that is going to be equal to then, so again, similar to the previous part here, it's going to be equal to, so just be careful here, right? Because we now know that n here is 291.55. So it's going to be 4 root 3 times n, but n here is 291.55, right? So what I get then is 291.55 times then 4 root 3. Okay, again, we're just basically using the answer from the previous part. The other thing that we need to adapt here then is the horizontal distance, essentially, or the perpendicular distance here, I should say, of x over 2 for this part, okay, which was originally the free cos 60 there, okay. So what do I get here? So this is going to give me, I'm just kind of doing this as I go here. So 291.55 times 4 root 3, that's going to give me 2020. So what else do we have then? So 25g times by 2, that's obviously 50g, which is 490. So I've got 490. And then 60g times x over 2, that's the same as 30gx, which is 294x. So plus 294x there. So subtract 490 from both sides here, and then divide through by 294, right? So as we can see, I've kind of run out of room here, which is always a problem of mine. What we get here then is 294x. So 294x is equal to, so that's 1,530, 1530. And then as we've just said, right, divide both sides by 294. And therefore x then is 1530, so 1,530 divided by 294. And that gives us then 5.2 here. Okay, so 5.2 meters there. So the distance AD, distance AD is equal to 5.2 meters. Okay. And there we go. So that's a solution to part B. And we're pretty much there now, people, right? Because we've just got part C to finish with here. I don't have a ton of room, so I'll probably just kind of narrate the answer rather than bothering to write it down here. It is just 1 mark, and, you know, these kind of like modeling assumptions here, you should just be familiar with the kind of required answers for these types of questions. So for part C, then it just says, state how you have used the modeling assumption that the ladder is a rod. So, because what I should really put here is a uniform rod, I'm going to adapt that. So I'm going to say a uniform rod here. Okay. So with the ladder being a uniform rod here, what we know then is the weight is going to act at a single point. Because it's a uniform rod here, then the weight is exactly in the middle of the ladder, right? So basically for the final part here, we're just saying that the weight acts at a single point, which is actually in the middle because it's a uniform rod. Another answer that you could give here is that the ladder won't bend. You could give that as a solution as well, but anything such as that is absolutely fine. Okay. So part C then, weight acts at a single point. Weight acts at a single point. Okay. And there we go. Apologies. My presentation is absolutely off the charts here for being atrocious, but it'll do. It'll do, right? So there we go then. That gives us the solution to part C and the solution to question 10. All right, so to finish with here then, as we can see on the screen, the very last question, question 11, is based on constant acceleration. So for this question here, what we're told then is a particle P is released from rest from a point h meters above level horizontal ground. Now, 1 second later, another particle Q is projected vertically downwards with this speed here from the same point from which P was released. Given that the particles reach the ground at the same time, what we want to do here then is just determine the value of h, right? 8 marks in total here for the very last question. Now, if you want to here, you can draw a diagram. That is absolutely fine. But for this question, I don't think it's really relevant. But if you want to, you can do that. That would be absolutely fine. But like I said, I don't think it's particularly necessary here for this question. But as we've already said, right, it's based on constant acceleration. So do that, okay? So I will make a note of here then is for particle P and particle Q. So for P here and for particle Q. Now, because we're looking at 2 particles here that are being dropped or projected downwards here, I'm going to take downwards as positive. Okay. I'm going to take downwards here as positive, like so. Okay. And for each particle here, we want S, U, U, V, V, A, apologies, is a little bit repetitive, and then finally T, okay? Each one here. So, as we said, right, taking downwards as positive here. So for S then, in both cases, because they both touch the same point on the ground here, they just reach the ground, right? We'll take the height here, or the displacement, to be h meters, right, as we're told here. So S then is h here, and the same is true for Q. Now for U here, that does change depending on which particle you're looking at. So for particle P here, as we're told then, it's released from rest. So for U here, for particle P, that is just 0, like so. And now for particle Q here, well, that's projected vertically downwards with this speed here. So U is 12.2 0.25 there, like so. For v, that isn't relevant for either of these two particles here, so we can kind of just cross that off if you really want to. Bosh, bosh, gone. Now for a then, so as we've already said here, we're taking downwards as positive here, so it's going to accelerate downwards. So a here is going to be positive g, or 9.8. The same is also true here for particle q, because we're not told otherwise here. So we just take g to be 9.8. Okay. And then for t here, just be careful with this, right? So for particle p, okay, that's going to reach the ground at, let's just say, t seconds. Okay. And then for particle q here, that's released 1 second later. Okay. So 1 second later, another particle q is projected vertically downwards. So for t here, that's going to be t minus 1. Okay, so just be careful for that. That's going to be t minus 1 there, like so. Okay, so based on the relevant information here for both of these two particles here, what constant acceleration formula can we use here? So we're going to use here s is equal to ut, so ut plus a half a t squared, like so. Okay, we're going to use this for both of these two particles here. So let's just start with particle p here. So for particle p, what do we have then? So s here is h. So h is equal to ut, so that's 0 times t, so that's just 0. You don't have to write the 0, but I'll do it anyway, just so you can see what's going on. Plus then a half times a, which is 9.8, times t squared. So t here is capital T, so times that by t squared, like so. Okay, 9.8 divided by 2 is 4.9. So what we get here then is h is equal to 4.9 t squared, like so. Okay, so now let's just do the same here then for particle q. So that was for particle p. Let's just highlight that. We'll now do the same here then for particle q. So for particle q here, again, just using the same formula here. So I'm going to get h again because I'm just using this equation here, right? So s is also h here. Now, what you might say straight away then is, can I not just replace it with 4.9 t squared? Yes, we absolutely can, and we're going to do that a little bit later on. But for now, I'll just keep it as h here, okay? So h is equal to, so it's ut, u is 12.25, t is t minus 1. So I'm going to get 12.25 times t minus 1, like so. I've then got a half, so 1 over 2 times a, which is also 9.8. So times it by 9.8, times it by t squared. So t here is t minus 1. I times it then by t minus 1 all squared. Okay. So now at this point here, I will replace h with 4.9 t squared. Again, if you want to do that on the next step, that's absolutely fine. But I'll just do it at this point here. So I've got then 4.9 t squared is equal to, so expand this out here then, I get 12.25 t minus 12.25. I've then got, so that's going to be 4.9. So I've got 4.9 times by this product here. So that's t minus 1 times by itself again, right? I'm going to get t squared. I'm going to get minus 2t. Yeah. And then plus 1 there, like so. What I would probably recommend there is that you don't try and expand something like that off the top of your head in your exam. I appreciate it's not particularly difficult, but it is very, very easy to make a silly mistake in an exam. And for example, just get the sign wrong. So just write it out as a full product in your exam, just to avoid any silly mistakes, hopefully anyway. So let's just simplify here. So I've got 4.9 t squared. I've got 12.25t, like so, minus 12.25. I've got 4.9 t squared, just expand out this single bracket here with this constant on the outside. So 4.9t squared. That's going to be minus 9.8t there. Like so. And then plus 4.9. Like that. So they will cancel straight away. What else am I going to get here? So 12.25t minus 9.8t. That's going to be 2.45t. I've got 2.45t. So that's them two dealt with. Minus 12.25 plus 4.9. That gives me minus 7.35. Minus 7.35. And that is equal to 0. Now, what I want to do here then is just solve for t, right? So add 7.35 to both sides here. So 2.45t is equal to 7.35, like so. Now divide both sides by 2.45, right? And therefore then, t here is equal to 7.35 all over 2.45. Throw this into your calculator if you can't see the answer straight away. But either way, we should get here is just 3, right? So t is equal to 3. Now we're not done here. We didn't want to find the value of t. I mean, we have to kind of find the value of t anyway, but that isn't what the question wants. What the question wants here is the value of h. Okay, so to finish with then, let's just go back up towards the top here. So to find h here, I'm just going to simply use then this equation here, right? H is equal to 4.9 t squared. And we know then that t here is equal to 3. So h then is equal to, as we've just said, 4.9 times then 3 squared. Well, that's just 4.9 times 9. And 4.9 times 9, that gives me 44.1. 44.1 there. And that's in meters. And there we go. Bosh. Beautiful. Okay. And there we go then. So as you can see, I don't think it's too bad. I don't think. Maybe not. Maybe disagree. Feel free to let me know in the comments down below. And as I said earlier on, you can draw a diagram if you want to, but I don't think it's particularly relevant for this question, but you might find it a little bit easier if you just draw a diagram at the beginning here, just so you can see then that both of the particles here are accelerating downwards, right? But either way, it's completely up to you. But you should get this answer here then of 44.1 meters. And there we go then. So that is the value of h there. Giving us a solution then to the very last question here for this paper, right? So that's all of the stats complete, and that is now all of the mechanics complete here. So before I conclude the video here, guys, as always, thank you so much for watching. If you made it all the way to the very end, I appreciate by the time you get to the very end here. It's a good 2 hours plus, and I am not the quickest at explain everything as I go. I do like to waffle, but there we go, right? So we've made it to the very end. Also, best of luck for paper 3 later on this week. And then finally, if you are looking for any more last minute revision here for A-level maths, right? So predicted papers, worksheets, additional revision videos, then head over to our website, AJMaths.co.uk, or you can alternatively become a member by joining the YouTube channel down below. For those who are on the revision tier, we will send you all of the predicted papers here for paper 3, right? So there's 4 papers in total. Give them all a go, and hopefully it should boost your revision then over the next couple of days. But there we go, right? So that is the solution to the very last question here. That brings us to the end then of this predicted paper here. So set D, paper 3. As I said before, right, thank you so much for watching. Best of luck with paper 3. And yeah, take care.